Hi, I'm Krishna Kumar. Welcome to CDMake 2021 International IFIP Cross Domain Conference for Machine Learning and Knowledge Extraction. Um, I'm representing the Great Learning Capstone team from India. Um, this is an 8-member team that developed this paper on deep convolutional neural network designed for pathology detection of COVID-19 in chest X-ray images. So this is a brief overview of today's presentation on this paper. Um, I'll go through this points. Here's a quick introduction. There's a with digital transformation. There's a huge amount of healthcare data which is available, and AI is really useful in these scenarios. With the AI's sophisticated algorithms, um, it's able to go through this huge amount of data and provide a lot of insights, which is very useful to the health professionals in the clinical practice. This is helping physicians to make better decisions, and in certain cases, it's even helping replace human judgment in certain areas like radiology. Today's main focus is detection of COVID-19 in X-rays. As we all know, COVID-19 pandemic has a devastating effect, since 2020. Um, and screening of COVID-19 quickly among the population becomes a very important subject. As you all know, we have very well-known tests like rapid antigen tests and RT-PCR tests, which is very widely used for COVID-19 detection. So in addition to this, we have alternate methods like uh, X-rays and CT scans also to detect COVID. Where do we use it? It's primarily used when both RAT tests and RT-PCR tests are negative, and the COVID symptoms are still showing up in the patient. We employ these mechanisms. So today's topic is primarily focused on how do we detect COVID-19 or other pathologies in X-rays using AI techniques. So we are primarily employing some of the deep learning methods, mainly transfer learning methods, um, in detecting the pathologies. So this is the model selection process that we have used. After the image pre-processing, we do the dynamic image augmentation, um, so that we make up for the less amount of images that has been provided for COVID-19. And after this, we pass these images to transfer learning algorithms one at a time, and we train these models, and eventually we test these models against the test data, and we use some important metrics like accuracy and F1 score to actually or actually grade the models. Um, um, After we do this, we select two best models, and then we apply some statistical methods to determine which model is actually performing better. In this case, we found that darknet 53 provided the best results for COVID-19 detection in X-rays. So let's see how we have done this. So really the first part of this process is actually data preparation. Um, and we didn't spend much time on this data preparation because all this data was available as open data sources. Um, so for normal and pneumonia uh, pathologies, we primarily relied on Kaggle. And in Kaggle, all all these X-rays were available with under uh, for SARS, MERS, and so on and so forth. So in the clinical settings, all these conditions or pathologies are classified under the class of pneumonia disease. Um, Secondly, we actually relied on some trusted sources for COVID-19 images, mainly the Cohen data source, which was available in GitHub. In addition to this, we also relied on few other GitHub sources and Kaggle sources. Um, uh, and on your right hand side, you can actually see some of the example of chest pathologies. As a layman and through the naked eye, it is very difficult to differentiate the different pathologies in X-rays. Only an expert radiologist could tell us um, what is going on here and what is the exact pathology. So in this paper, we are attempting to see if our transfer learning methods um, in deep learning, can they help us in accurately finding the pathology. The next step after the data preparation is the pre-processing. So we ensure that before we feed the images into the training, both the left lung and the right lung images are properly presented. So from that perspective, we are eliminating all the X-ray images where only one lung information is shown or only the lung information from side positions are shown. The model cannot infer much, and hence we are eliminating these images even before training. Subsequently, we are applying grayscale to these X-ray images. Many experiments and studies have shown that when we apply grayscale on the X-ray images, the accuracy of the model drastically improves. So we have applied these two pre-processing steps and before splitting the images into test and train sets. Finally, we apply the model selection. So in this process, we are taking this pre-processed images and passing it through the transfer learning nets one at a time, and adding few fully connected layers and um, training them and eventually testing them against the standard test data. As you see here, starting from a custom CNN where the accuracy was very low, as we applied more basic to sophisticated transfer learning methods, we have achieved pretty high accuracy. Mainly, I want to highlight on the ResNet 50 and DarkNet 53, where we have achieved an accuracy greater than 90%. Moving on, once we found that DarkNet 53 is able to give a relatively better accuracy than other models, we did a number of tests or hyperparameter tuning and arrived at the best configuration that gave us the best results. So this is depicted in the left-hand side. This is having a one fully connected layer, and we used stochastic gradient descent as the optimizer with a learning rate of 0.001. With this, we are able to achieve good accuracy of 95.3% on the test data, and we were able to decipher uh, the pathology of the image in around 50 milliseconds time, which is pretty good. On your right hand side, you are able to see the DarkNet 53 detailed architecture. This consists of 52 convolutional layers, and this is actually derived from a framework called as YOLO V3, which is mainly used in the object detection. And in the object detection, darknet 53 is a classifier, and we took that classifier as part of our study for classifying the different pathologies. So this slide depicts the model metrics. On your left-hand side, you can see um, the amount of training and test data that we have used, um, and also the pre-processing specifications or the parameters that we have used. One highlight here is that you see that our class of interest is COVID-19, but the number of images that we have provided for training is really, really less. To address this, we applied dynamic image augmentation, which actually takes existing images and does few changes like rotating the images by a few degrees, zooming in, zooming out, doing some shift in the uh, images. And even in those conditions, the model should actually learn that learn to get the right pathology. So what we observed is by doing this augmentation technique, um, for all the models, we are able to generalize the model well, and the model is able to identify the correct pathology um, even when the X-ray images are slightly changed, which is expected in case of test images. On your right-hand side, we can see that we have reported the uh, performance of all the models. The main models that have given us good accuracy is ResNet 50 and DarkNet 53. What we observe from these results is that DarkNet 53 is giving very good results, mainly because it uses the ReLU, leaky ReLU activation with the residual network. This is actually helping in uh, improving the performance. It is able to spot the COVID-19 patterns much better compared to other algorithms. To justify this, we have also done some statistical tests, which you will see in the future slides. So this is a very brief overview of the hyperparameter tuning that our team did. Once we identified darknet 53 is yielding good results, we did a deep dive and did a very extensive hyperparameter tuning with a number of parameters, like number of fully connected layers, the optimizer type, for example, Adam, SGD, and so on. And we have depicted the 6 tests that have given good results. We particularly wanted to highlight the last one, test number 25, where we have achieved the highest accuracy and F1 score. Coming to the model output, we've highlighted the confusion matrix. As you see here, the darknet 53 has given us a very good result with a precision of 0.97 and a recall of 0.88. The overall F1 score being 0.95. Few highlights, from the slide is the first table depicts that even with very less COVID images in training, we were able to darknet is able to really get a good score, whereas other models are still struggling in the range of 0.0 to 0.2 F1 score. In phase 2, we got more number of images, and we saw that all the models started picking up the signals, and they're performing better. And the darknet 53 is performing even better than some of those models. So some of the key takeaways here is that as you provide more training images and address imbalance, your model is going to perform better. Another key observation is that higher resolution images yield better results. And finally, darknet 53 is performing well even in very adverse scenarios, like when your class of interest is um, very less or imbalanced. It is still able to perform in those scenarios as well with the dynamic image augmentation. Um, Finally, we took two best models, and we tried to dig in and find out if which classes are um, performing better, or which classes are performing the same. So as you see here, between ResNet and DarkNet, um, the DarkNet is better able to spot the COVID-19, and ResNet is actually uh, largely determining even some of the COVID-19 images as pneumonia. And we use the McNamara-Boker post-hoc test to validate this. The third row depicts that um, darknet is better able to differentiate uh, the COVID-19 images, and hence it is more skilled to perform this task. Some closing reflections. AI is really helping the radiologist in this case um, to rapidly detect the COVID-19 in X-rays. Um, and it is doing this very efficiently, um, and with a very high accuracy in a very time-saving fashion. So our recommendation is darknet 53 is more suited for the X-ray use cases in pathology detection, even when there are imbalanced classes present. Um, to get to this point, we had few challenges. Getting X-ray images certified from a radiologist takes time. Also, applying some of the filters in a manual fashion takes time. But all these are finally coming up well. When we actually put the model and get the results. Um, some limitations of this model is it is trained to see both the lungs. So when you're providing only one lung information, um, the model may perform very poorly. Um, Secondly, this model is not trained on CT images, but we can use the same architecture to train on CT images, and we could use the same model architecture to detect COVID in CT scans as well. This study has taken the data mainly from three continents, mainly North America, Asia, and North America, Asia, and Europe. We believe that this model is still biased. If we include images from other geographies as well, we could reduce the bias, and we could use this model globally. Um, the X-ray images in this study has been very sparse. Um, the COVID-19 disease is such that the pathology changes between day 1 to day 10. And there is a possibility that some of the days of infection is not captured properly in this X-rays, and hence it and hence the model is not trained on those days, and it could result in missing this pathology in the end detection. Our proposal is to ensure a uniform distribution of COVID-19 images spread across the days of infection. This could lead to much better accuracy, and this is the area of research for future. With that, we are coming to the end of this presentation. We thank our professor, Dr. Narayan, and our mentor, Abdul, for guiding us through this capstone, and Mr. Anwesh for helping us in paper submissions. We also thank all the online materials and papers and the blogging materials that we figured out during the course of this paper. Thank you.